Now, let's understand one of the important communication models in distributed computing called shared memory. Imagine that instead of computers sending message to each other, they all access the same storage area. That common storage is called shared memory. Whenever one processor writes some data into this shared memory, the other processors can immediately read the updated information. This makes communication much simpler because processors don't need to exchange separate messages. A good real time example is shared Google document. Many people can edit the same document simultaneously and everyone see the latest changes. Similarly, in shared memory system, processor work together with using the same memory space. So, this is the diagram for on-chip memory. Here, the figure shows how memory can be organized inside a computer system. On the left, we see a traditional computer where one CPU is connected to its memory. On the right side, multiple processors are placed the same chip package. Instead, each processor having completely separate memory, they can share same physical memory. Because the processors are located very close to each other on the chip, communication becomes much faster compared to sending information over a network. This architecture is commonly used in modern multi-core processors where several CPU core works together efficiently. So this is a bus-based multiprocessor. Now let's see how multiple processors communicate using a shared bus. In this architecture, all CPUs are connected to a single memory through a communication bus. Think of the bus as a common highway. Whenever any processor wants to read or write data, it uses this highway. The advantage is that every processor can access the same memory. However, when many processors try to use the bus at the same time, traffic congestion occurs. This limits the performance as the number of processors increases. So, while bus based systems are simple and cost effective, they are suitable only for a limited number of processors. So, we are going for next. So, here to improve performance, processors are provided with their own cache memory. A cache is a simple, very small but extremely fast memory located close to the CPU. Instead of accessing many memory every time, processor first check whether the data required is in the available of the cache. So catch. If it is available, the processor gets the data much faster. But this creates another challenge. If one processor changes the data in its cache, the other processors may still have old value in their cache. Therefore, we need cache coherence protocol to ensure that every processors are always see the correct up-to-date data. So, so next is write-through protocol. One of the method of maintaining cache consistency is called write-through protocol. Here, whenever a processor modifies data, the updated value is written both to cache and immediately to the main memory. This ensures that memory always contains the latest version of the data. For read operations, if the data is already present in the cache, it is used directly. Otherwise, it is fetched from memory. Whenever a processor updates a cached value, other processors invalidate their outdated cache entries. The main advantage of this protocol is simplicity and data consistency. However, since every write operation updates the main memory, it generates more memory traffic and reduce the performance. So next we are going to see about write once protocol. Another cache coherence method is the write once protocol. Instead of updating the main memory after every write, this protocol allows repeated modification to remain inside the cache. Each cache block can exist in one of three states: invalid, clean, and dirty. A clean block means both memory and the cache have the same value. A dirty a dirty means the cache contains a newer version than the main memory. This approach significantly reduces unnecessary memory updates and lowers bus traffic. As a result, the processor can perform repeated write operation much faster. So this is the example for write once protocol. The figure explains how the write once protocol works. Initially, one processor reads the data and multiple caches may store the same value. When a processor A writes a new value, the processor detects this update and invalidates their old copies. So processor A now owns the latest version marked as dirty. Further modification happens only inside processor A cache without accessing the memory repeatedly. Later, if another processor requests this data, the latest value is supplied and ownership is transferred accordingly. This mechanism keeps all processors synchronized while reducing unnecessary memory operations. So, another one is called ring-based multiprocessor. So far we discussed processor connecting using a SAD bus. Now let's look another architecture called ring-based multiprocessor. Here processors are connected in a circular ring instead of sharing one common bus. Every processor has its own private memory and cache. When a processor needs data that it doesn't have, it sends a request around the ring. The request travels from one processor to another until the data is found. This doesn't reduce the congestion because communication is distributed around the ring instead of depending on one shared bus. Next, we are going to see about the read protocol. Now, let's understand how a read request works in the memnet architecture. When a processor wants to read a memory block, it first checks whether the block already exists in the local cache. If it is available, the read operation finishes immediately. If not, the processor waits for the communication token and sends a request around the ring. Each processor checks whether it has the requested block. The first processor that finds it plays the data into the request packet. When the packet returns to the requesting processor, the block is stored in its cache. If there is no free cache space, an old block is replaced based on the protocol rules. So next one is the write protocol. Finally, let's see how write operations are handled. If the processor already has the only copy of the required block, it simply updates the value locally. If other processors have also have copies, an invalidation message is first sent around the ring. This forces all the processor to remove their outdated copies. Once the requesting processor becomes the exclusive owner, it safely updates the data. If the block is not available locally, the processor first retrieves it and then invalidates other copies before performing the write. This process guarantees that only one processor modifies a memory block at a time, ensuring consistency across the entire system. Thank you.